Hello everyone, welcome to another video session class. So in today's class we will study about azepines, the synthesis of azepines, reactions and medicinal uses. So see the structure of azepine. This is the structure of azepine. So it is a nitrogen containing 7-membered ring. It is a nitrogen containing 7-membered ring heterocyclic compound. So you see this nitrogen 1 2 3 4 5 6 7. Okay, so it's very important. So azepine is a nitrogen containing 7-membered ring heterocyclic compound. So, and you remember this structure is not aromatic, okay, because 1 2 3 4 5 6, then here nitrogen lone pair 7 8, okay, 2 electron will be there, so total 8 electrons are there, delocalized electrons are there, so it is not following Huckel rule at all. Okay, so aromaticity, about aromaticity is not aromatic, okay, you remember. So boat conformation with chair 22% with chair conformation, and most of the structure will naturally available as a boat conformation, that is 78% is boat conformation and 22% chair conformation, that means both conformation are more stable. So planar azepine N is sp2 hybridized, okay, have potential 8 electron system cyclic, and planar with 4 and pi electron is anti-aromatic character, least stable. Okay, thus azepine and its tautomers exist in non-planar conformation, both conformation, one atom with sp3 hybridized. Okay, so here you see, so this compound do not comply with Huckel rule. We know it is not complying with this Huckel rule, that is 4n plus 2 pi electron, because 8 electrons are there, okay, pi electrons are there. So if you are taking n as 1, so it is 4 into 1 plus 2, that is 6 pi. If you are taking n is 2, that is 4 into 2, that is 8 plus 2 10. Okay, so 6 or 10, but it is falling in between, that is 8. So azepine is non-aromatic compound, so it is not aromatic compound, you remember. Then tautomerism. So tautomerism may possible because of this hydrogen, okay, this hydrogen may shift, red hydrogen may shift from one place to another place. So 1H, this in one position hydrogen is present, then 3H in the third position, 1 2 3, then 4H, so fourth position, from here 1 2 3 4, fourth position, then 2H. Okay, so among this one, stability order is 3H will be most stable, 4H will be next, and the 1H will be the next. Okay, stability, that is 2H is not at all stable, okay, least stable. The next, balance bond stem. So next is the synthesis. How can we synthesize this azepine? Okay, so first is balance bond isomerization, organization accompanied by change in aromatic distance and bond angles. So you see, we are using benzene and ethyl carbonazidate. Okay, carbonazidate. So azide, we know N3 is azide, so it is ethyl carbonazidate. Okay, in presence of light, Hp. So N2 will come out, and ultimately this N will attach with this 2 carbon, okay, with this 2 carbon. So there will be organization of the bond. You see, this bond will break down, it will go this side and this side. This bond, half bond will come here, half bond will come here, this half bond will come here, bond electron will come here, this one electron will come here. So one bond will form here, next bond will form here, and next bond will form here. So ultimately we will get a structure like this. Okay, 7 member. Okay, C double bond O, C2H5 is still attached to this carbon. So we will use one base, OH negative hydroxyl, so that will take up C2H5COOH. okay, carboxylic acid group will come out. Okay, then next what will happen, isomerism will take place to form 3H azepine. So ultimately we are getting one azepine. Okay, this is also azepine. Bond reorganization and reorganization of sigma and pi electrons without rearrangement of atoms. So atom is not rearrangement, there is no atom rearrangement taking place here, only the bond breaking is taking place. Sigma and pi, single bond and double bond reorganization is taking place to give this product. Next, from phenyl azide, so you see this is phenyl, then azide N3, so heat N2 will come out, so N, this nitrogen will form a bond with this carbon, this bond will break down, this will come, this bond will break down, one part will come here, okay. So ultimately we are getting this one, okay, benzaazirine, okay. Next, C2H5NH, okay, amine will attack, so ultimately this bond will break down and this nitrogen will attach to this carbon, okay. So you are getting 1s azepine derivative, okay. So ultimately this is the same structure, correct, this is the same structure. After that one, isomerization will take place, so hydrogen will move from this position to this position, and we will get 3H azepine derivative, or 2-diamino 3H azepine, okay, 2-diethylamino, okay, diethylamino 2-diethylamino 3H azepine, because 3H means in this position from original azepine structure one hydrogen is added, okay. If you are from in parent structure, if you are adding one hydrogen to any place, you have to give the position 3 and you have to give, you are adding one hydrogen, okay. Next, synthesis from nitrobenzene, so you see nitrobenzene, you deoxygenation of nitro group by tributyl phosphine, so it is tributyl phosphine, okay. So it is deoxygenation, this oxygen will remove, so N will be remaining. Again, next what will happen, nucleophilic addition of alkoxy group to aryl nitrine, okay. So here one alcohol will attack, so this bond, you see OR bond will form with this one, then N, this carbon bond, one bond will form, okay. So ultimately we are getting this structure N negative. So next, rearrangement of the bond will take place, you see this bond will break down and come here, okay, and OR will remain at the same position. So you see here, after breaking this bond, it is one new bond is forming here, another will be in this position, so one bond, another bond, this bond pair electron will taken up by this carbon, so it is negative charge, okay. Next, what will happen, so it is same, okay, correct, this structure and this structure same, N, then NCOR, okay. Then next, one protonation will take place, to give 2 alkoxy 3H azepine, okay. One protonation will take place at this position, okay, at this position. So ultimately this negative charge of this carbon will be compensated by this H plus, and ultimately we will get alkoxy 3H azepine. Next, reactions, first terminal reaction, so if you heat at 200 degree, N carboethoxy 1H azepine will convert to N phenyl carbamate, okay. That means the from 7 member ring to 6 member ring, okay, 7 member ring to 6 member ring. Then ring contraction, orbital symmetry control disrotatory electrocyclic process, so you see, you in presence of UV light, you apply in presence of methanol and UV light, this compound will form a electrocyclic process, that means this ring will break down, this rotation will take place, and ultimately you will get fused ring, okay, two ring are attached, okay. So N is at the same place. Then next, see this bond will here, bond will form between this carbon and this carbon, okay, this carbon and this carbon, so total 4 member ring this one will form, okay. This bond electron will come here, this bond electron will come here to form a bond here, okay, and ultimately you will get this structure. Next, dial-Elder reaction, so it is, see here it is Diels-Elder reaction, so this N substituted, there is carboxy substituted compound, so here you react with this one at 80 degree benzene, so you will get ultimately this compound, okay. So this is another reaction, C6H5, so you see C6H5, this one is red one is here, okay, correct, N is there, So ultimately from here one bond C, this carbon and this carbon, one bond will form here. Okay, this carbon and this carbon, one bond will be formed here, and along with this carbon this ring will attach. Okay, this ring will attach. So ultimately you will get the final compound as this one. The next reduction, so reduction of the substituted ring azepine ring to NN dimethyl 3H azepine. If you react with 5% PDH2, you will get 3,4,5 tetrahydroazepine. So 3,4,5 tetrahydro, that means in 3 position, 4 position, 5 position we have added 1 hydrogen. So another will be 3,4,5,6,7 pentahydroazepine. Okay, pentahydroazepine, that is substituted azepine. So you will get both these two. Then oxidation, so oxidation of the substituted azepine like 2N and dialkyl 1H azepine. So in presence of O2 oxygen oxidation, NHR2 will come out, NHR2 will come out, and ultimately you will get azotropane. Okay, so it will be oxidation take place at this position, this carbon, correct? C double bond O. Earlier it was Nr2 dialkyl, but now it is C double bond O. So this is the oxidation reaction of azepine. Next, medicinal uses. So it is anticonvulsant drugs such as carbamazepine, oxacarbazepine. These are containing the basic structure as azepine. You see this structure is azepine, this structure. Okay, middle structure is nothing but the azepine. Then tricyclic antidepressant or TCA, example imipramine, desipramine, clomipramine, trimipramine. So this is the structure of imipramine. So this is containing the basic structure as azepine, okay, with two benzene ring fused together. So next, medicinal uses. It is also used as an anesthetic agent. Okay, some of the derivative of this azepine are used as anesthetic agent. Its derivative are also used as anxiolytic, that is to reduce the anxiety. The drug used for reduction of anxiety, and also for hypnotics, that means to induce sleep, okay, in person. So those for those purpose this azepine derivatives are also used. Okay, so I hope you have understood. Thank you.